Hi gentlemen. Today we'll be discussing the wave properties of light and the electromagnetic spectrum. This is the beginning of the optics unit. So we're going to start dealing with light and how that affects our eyes, how we see, and where light moves and travels. Okay? So the first thing to understand is light acts sort of like a particle and a wave. Okay? It's an electromagnetic wave that has a distinct range of frequencies and wavelengths. So light specifically has a wavelength between 400 and 700 nanometers. So let's talk about what a wavelength is. So light travels something like this. If you look here, just like a wave in water. Okay? Moving up and down, and here you can see at a much quicker pace. Okay? So the length of a wave, which goes from what we call a node here to a second node through a peak and a trough. So one peak and one trough basically equals a wavelength. It's the length of one full wave. You go up and back down again. Okay? So this here is your wavelength from there to there. Okay? Also from here to here or here to here. Okay? So it contains one peak, one trough, and two nodes. That's one wavelength. Okay? The intensity or the amplitude tells us how bright that light might be, so that's basically the height of it. The length of the wave gives us more of the idea of color. Okay? So the relationship here between wavelength and frequency you can see below. Wavelength deals with distance, sort of the length of the wave. Frequency deals with the time, basically how quickly that wave moves. And generally you see as wavelengths, sort of longer wavelengths have low frequency, they don't move that much, but as you get into longer or shorter wavelengths, you get much higher frequency. There's a lot more movement going on. You can see this tends to be more intense, and that was gross. Okay, so that's your relationship here between wavelength and period, which is dealing with frequency. Okay, so basically the wavelength, when you're dealing with time, you're dealing with periods. Okay? So when dealing with that, basically the wavelength in seconds per cycle, so basically how long it takes to do one wavelength gives you that frequency, and that is also called a period. So the time it takes to do that one wavelength we call period. Okay? The different wavelengths of electromagnetism give us different types of waves or rays. Okay? So the longer it is, the longer a wavelength. We usually use this symbol here, which is wavelength. We call that lambda. So lambda equals wavelength, but a longer wavelength equals less energy. So shorter wavelengths or higher frequencies create more energy. So things like gamma rays have a lot more energy because they have much shorter wavelengths than things like radio waves, which have much longer wavelengths. Visible light, so light we can actually see, falls right in here in this distance of 400 to 750 nanometers. And that's important to understand. Okay? That length deals with energy, but also tells us the type of radiation that we're dealing with. So the microwaves have the least amount of energy, then we're microwaves, infrared, then visible light, then we're talking about more energy, things like ultraviolet, which is why we see things like sunburns from the sun, right? This is the UV light that we get from the sun that creates that sunburn. So that increase in energy causes an issue. Talking about X-rays, same sort of idea. Okay, X-rays send a lot of energy through your body, but they reflect, or they don't bounce, they don't go through your bones, and so that reflection of the X-rays back from the bones gives us an idea where your bones are, and that's how X-rays work. And then gamma rays are released, have the most energy, and that's what you see released when we talk about radioactive decay and radioactive radiation from atomic bombs. Okay. So again, here you can see that spectrum, and here's that visible light. So you're talking In the 400 range, you're talking about things like purple and blue. Okay, so those longer wavelengths, or shorter wavelengths, more energy. And in the longer wavelengths, the 700 to 750, you're talking about reds and oranges and things like that. Okay, so it's important we understand the visible light spectrum here. We can actually remember sort of this spectrum using Roy G. Biv. Okay? So these longer wavelengths with red, orange, yellow, green, blue, indigo, violet. And that gives us sort of that spectrum from 750 all the way to 400. So that there's an anagram to help you remember that. So this here is a reverse of the one above, just so you don't get confused. Okay, but again, important part here is 400, shorter, more energy, we're talking purple. Red, 750, less energy, longer wavelengths. Okay. So again, we just talked about the X-ray. Okay, you're not actually seeing your bones, you're seeing that reflection of the X-rays bouncing off your bones. So quickly, we'll talk about the different types of radiation, starting with radio waves. Okay, we hear those on the radio. They're used to send signals long wavelengths, so they travel over long distances. Microwaves actually have a little bit shorter wavelength, still longer than light. Interestingly enough, people talk about how dangerous they are. They actually have longer wavelengths than light, less energy than visible light. So really not that dangerous as you might think. Infrared wavelengths, we use that to see in the dark. So again, the longer wavelengths allow us to see heat and pick up that night vision. You know, it picks up heat rather than light, so it reflects off that heat. You can see heat using infrared. Visible light we talked about, 400 to 750 nanometers, which is distances, really, really tiny distances. Okay, ultraviolet light, we use that, okay, to see, well, we get that from the sun, okay. The sunscreen that we use actually absorbs that and keeps it from damaging our skin, but it's also used to view or to check dollar bills to see if they're actually counterfeit or not. So we can see that actually in older bills. X-rays, again, we use that for imaging of bones. Again, much shorter wavelengths, more energy, and last but not least, we have those gamma rays, the most energy because they have the shortest wavelengths. Okay. So how does this all help us see? How does it create colors that we see? Okay. And so the white light that we see in a room is actually made up of all the different wavelengths of light. So if you remember, again, our spectrum here, red, orange, yellow, green, blue, indigo, and violet, all correspond to different wavelengths of light. But if you combine them all, you get white light. And that's what prisms, or sometimes you see when you're in your kitchen and light travels through the window and it breaks up into those small little rainbows that you see. It's breaking up into its parts. So white light is all light combined together. And that's why it can be broken up into those parts. And that's how prisms work as well, breaking things up into their parts. Okay, so we have two, and that sort of follows what we call the additive color theory of light. And this deals with light in air, as light travels through air. So you can see we have three primary colors, red, green, and blue. And when those three primary colors combine, they create white. But you can also get secondary colors. So for example, if you combine blue and red, you get magenta, blue and green you get cyan, and red and yellow you get green, or red and green you get yellow. Okay, and different combinations and different amounts of each one give you the different colors of the rainbow. So you can check out these two applets here. The first is pretty straightforward, right? You combine the red and the green, you get cyan, the red and the blue you get magenta, the red and green you get yellow, and all together you get some white. So it gives you an idea here of the different amounts. Now the second one actually shows you how you can get sort of different colors as well. Mine's not working, I'm going to have to update this, but you can actually play around with that one and see the different, that you can use different amounts of red or blue to get different shades of that purple. And this is where we get things like orange and indigo when you start combining different amounts. So that's the additive color. As you add these colors together in air, right, they combine to create new colors. On the other hand, subtractive color theory deals with things we see like shirts and desks, right? Things that we see physically. They actually reflect light, and it's the reflection of light that allows us to see them. right? So if you look below, when we see the color cyan, we don't see this color. What we're seeing is the reflection of blue and green light to our eyes. So up here, you can picture our eyes, right? Receiving the blue and the green. The red is absorbed by cyan. Okay? So when we see, for example, red, right, what we're seeing is white light hitting the red, but only red light being reflected off and all other light being absorbed. So it's the reflection of certain amounts of light or colors of light that allow us to see colors. Okay? So again, magenta, because it's made up of red and blue, according to additive color theory, when you add those those colors together and they hit our eyes, we see magenta. Okay? So all subtractive color theory is talking about is magenta absorbing green, subtracting it from the white light, the red and blue reflecting, and us seeing those colors. Okay? And again, we talk yellow, because it's made up of red and green, blue light is absorbed, and our eyes see yellow, because the red and green combined, added together from additive color theory, allow us to see yellow when blue is subtracted, thanks to subtractive color theory. So again, looking at the interactive Java applet, and you can see now these are the secondary colors from additive color theory, the magenta, yellow, and cyan, become the primary colors in subtractive color theory. And now we can start seeing, as we combine cyan and yellow, we see green. You know, we combine cyan and yellow, we see red. And when we combine cyan and magenta, we see red or blue. So the actual primary and secondary colors flip versus additive and subtractive color theories. Okay, so make sure you answer the Verso question and come to class ready for a quiz.